Okay, so now that we've talked about valid computation histories as strings, we're next going to talk about them as languages. So we're going to talk about the language corresponding to all of the strings which represent valid computation histories of a particular M running on a particular X. Okay, so let me give you that definition. So we define given a Turing machine M, and so the Turing machine M is accompanied by, remember, some states, the tape alphabet, an input alphabet, and so on, right? I'm just not writing out the 9-tuple. And an input string X, right? And an input string X. Let me just write X and sigma star. And so what we need to define valcomps, the language corresponding to all valid computation histories, is an alphabet, right? And in this case, the alphabet isn't going to just be gamma, or it's not just going to be sigma. What we need as an alphabet, we need an alphabet which allows us to define strings that look like this, right? So those strings should contain letters in the tape alphabet. They should also allow us to use letters where we're interpreting states as letters. And it should also allow us to use the hash, because remember, we're assuming that the hash is not in gamma and, of course, not in Q. And so then what we're going to do is we're going to define the alphabet delta as gamma union Q union the hash. Okay. Okay. And so this is our alphabet over which we're going to define valcomps. So valcomps is a language which, given a Turing machine M and some input string X, returns. So really it's more of a function which returns a language, because valcomps given a different Turing machine and a different input string X could be different, most likely. And in this case, we define this as the collection of strings alpha over the alphabet delta, where alpha is a valid computation history of M running on X. Okay, so take a Turing machine M and an input string X and run M on X, right? And all of the strings that represent the valid computation histories, place them in valcomps. And there's an extremely important remark to make about valcomps, is that since we're dealing with M being a deterministic semi-infinite tape Turing machine, there are really only two options to valcomps MX. There are only two options to valcomps MX. So either the cardinality of valcomps MX is 1. Okay. So it'll be 1 if M is running on X and at some point it halts, right? It has to be exactly 1. It has to be exactly 1, because if it were more than 1, then at some point, the valid computation history would start with the starting instantaneous configuration, and then it would keep going, would go through all of the alphas, and then at some point it would diverge, right? So then you have two different strings which represent two different computation histories of M running on X, but that divergence means that at that point, M had a choice in its transition function, but by determinism, that's impossible, right? And so this is only possible if M halts on X. if M halts on X. And so the other possibility, the only other possibility is when M loops on X. Well, when M loops on X, you can never write down that finite string, right? There's never that alpha n, there's never that halting instantaneous configuration. And so then valcomps mx, by definition, right, because the definition is that this string is a valid computation history, but to be a valid computation history, you have to respect all these four conditions. And so if you have an infinite string, sure, maybe these three conditions are being respected, but you never get to a halting instantaneous configuration. You never get to an alpha n, right? And so then you can never meet the necessary and sufficient conditions of the valcomps set, meaning that you never add a string into valcomps, and so it remains empty. Okay. And so that tells me that M loops on X if and only if the size of valcomps is 0, or in other words, valcomps is empty. Right? M loops on X. Right, and so we can tie this back to the previous example of the Turing machine we were looking at. So in the previous Turing machine M, right? Valcomps M given X as ABB. That was the language, right? This was when M halted on X, and that was the language containing a single string. And that string was this first alpha 0, and then the second alpha 1. Okay. And this is a single string, right? So I think maybe this is confusing to some students. This is a single string. Single string. But it's composed of, substrings, like any other string. Okay. And so this is when M halted on X, right? So M was deterministic, and so if M halted on X given some input, it could have just been that valcomps was of size 1 and only 1, right? The reason why we're dealing with valcomps is because, in general, if you were dealing with an arbitrary Turing machine which didn't have any requirements on its specification, then maybe it could be non-deterministic, and in which case valcomps could be more than 1. But in this case, for simplicity, we're just restricting ourselves to deterministic semi-infinite tape Turing machines, because all other Turing machines are actually equivalent to deterministic semi-infinite tape Turing machines. Okay, so that was when M halted on X, in particular M halted on ABB. When given a string on which M looped, so M given X, I think it was BA, then M would start churning through the computations running on AB, and it would never halt. So you can never write down that string using a finite number of letters. And so this would remain empty. Okay, so at this point, you're probably thinking, what does this have to do with the actual objective of this lecture? Because remember, the objective of this lecture is to show that the not halting problem mapping reduces to the all CF problem. Well, valcomps is actually extremely useful to do this because of the following key observation. So the following key observation is necessary to make. And it's that, like we've just discussed in the previous remark, M loops on X if and only if the size of valcomps is 0. In other words, valcomps is the empty set. Valcomps of MX is the empty set. Okay, so at this point, this equality isn't really all that helpful, because remember, all CF, the all CF problem, it asks given a context-free grammar G, which I'll write this out explicitly actually, is a 4-tuple of variables, a start variable, a set of terminals. So this is the set of terminals. So to make things more explicit, I'm using T instead of sigma, just to avoid a bit of confusion here. And so it's given a context-free grammar G is L of G generating all possible strings of terminals, right? So if at this point we think, well, we should create a context-free grammar G which generates Val-comps, that's probably not even going to be very helpful, because what we need to do is we need to check an equality for something star, right? For a universe of strings. So this equality isn't all that helpful. And actually, mind you, you probably wouldn't be able to create a context-free grammar G. Actually, you certainly won't be able to, because Val-comps is not context-free itself. Okay. But what is context-free and what does relate back to this RCF problem is if we apply the complement to both sides. So if we apply the complement to both sides, then by set theory, we still have an equality. So we have an equality of sets. And in this case, if I complement the empty set, I get, well, the universe minus the empty set. In our case, the universe now is delta star, right? It's delta star because Val-comps is a subset of delta star. Right? And so this is equal to delta star. Okay. And that seems to line up pretty well with what the solver of an RCF problem would say if it would say yes, right? Or no. So a yes instance would be, well, the language generated by G is T star. Well, what if we just make G generate Val-comps complement, right? And then we check using the solver whether it is yes equal to delta star or no not equal to delta star. Well, it turns out that doing that effectively produces or creates a not halting problem solver. Okay, how is this possible? Well, let me show you a diagram. So this is a diagram which hopefully you're very used to by now. So consider an instance of the not halting problem, Mx. And suppose I feed this into the instance modifier im. So I feed this into im, okay? And what I'm going to do is I'm going to design an instance modifier such that given input mx, it's going to produce as an output a grammar, right? So it's going to output a grammar. So the instance of the RCF problem, in other words, which is just a grammar. But I'm going to design this grammar in a very specific way. I'm going to design this grammar in a way such that, so G is created such that it generates Val-comps complement. Val-comps complement, because checking for Val-comps complement is equal to delta star is equivalent to checking whether M looped on X. Okay, and so then if we pass this to our RCF solver, to the RCF solver, then if our RCF solver says yes, right? So if the RCF solver says yes, so the answer to the instance of the RCF problem is yes, well, this implies that L of G, which is equal to Val-comps mx whole complement, is indeed equal to delta star, which implies via this relation, right? So via this relation, that Val-comps mx is empty. The other way to see this is, you could apply the complement again. And the complement applied twice gives you val-comps, and the complement applied to delta star is the empty set. And now we said in the previous remark, that when val-comps is empty, right? The key observation is that that means that M loops on X, right? Because we can't actually write down in a finite number of letters the computation history of M. So M loops on X, which means that this yes actually maps back to a yes instance for this arbitrary instance of the not halting problem. Right, so the answer to the not halting problem is also yes. Okay. And so we have a yes to yes. We can also show that we have a no to no. So if we get a no here, so if the answer to the instance of the LCF problem is no, then that means that I'm going to skip a few steps. I'm just going to say that that means that val-comps mx is not equal to the empty set. Which means that val-comps, right, the language containing valid computation histories, has at least one finite string, right? Strings are finite in our case, okay? And so that means that it has a string where there's a halting instantaneous configuration at some point. Okay? So that means that at some point, M halts on X. And so then the answer to the instance of the not halting problem is no. Right? Because M does not loop on X, meaning that it halts on X. Okay. And so this is why we've gone through this sort of rigmarole, as some would say, where we're defining valid computation histories and the language of valid computation histories, because that allows us to define the complement. And now if we are able to create a context-free grammar G, which generates val-comps complement, then we effectively have, right? So this effectively acts as a, let's see. So this thing here effectively acts as a not halting problem solver, right? So then it couldn't be that the LCF problem was decidable, because if it was decidable, then we could go through this rigmarole of a procedure, to solve the not halting problem, which is impossible because it's undecidable. Okay? So that is why we've been talking about valid computation histories and val-comps, the language of valid computation histories. And so now all we need to do, all that's left to show. So, right. So all that's left to show is that, well, if we do show that val-comps complement mx is context-free, then we will have shown that the not halting problem mapping reduces to LCF, which will imply that LCF is undecidable. Okay, and so that's what we're going to do for the remaining of the lecture videos, I suppose, is we're going to show that we can actually create a context-free grammar. In fact, we're going to design a PDA, which is, can be converted to a context-free grammar that accepts val-comps whole complement. Okay, so that's what we'll do in the next few videos.